So you can see what we have. Okay, so this is our work area. So we've got some computers that people can use for data processing. They were on site. Some of our beamline control computers. And then these three monitors are the ones that you see when you're doing your data collection. And I think when Robert does his, he can share his desktop and you can see more closely what's going on. And just to give you a quick example here. So I've aligned the beam line. And so that little green fluorescent blob there is the beam that's being, we've got a fluorescent crystal in the beam line so that we can visualize where the beam is hitting. Just as verification that we're actually have the beam aligned. Oh, there's Vivian. And so we're going to walk up to one of our end stations. I'll show you what's inside of it. So all the stations are made out of these heavy steel panels that have lead inside of them. And so inside the station, the X-rays come through the wall there and come down this pipe through all this various conditioning equipment. And one of the first important things that they'll hit is this device right here, which is called a monochromator. So the X-rays that we get out of the storage ring are not a, well, look at it, think of it as light, a single color. So we get, you know, what we call like white beam or pink beam, and then we need to select out of that a energy or frequency of radiation that we want to use. And the monochromator does that by having a crystal in it that the X-rays hit, and then the angle of that crystal relative to the incoming X-rays will select out the energy that you want and then allow it to be transmitted down the beam line. And so it'll then exit the monochromator, go through some more conditioning elements, and then the next interesting thing we have is in this large tank here, which is we have an X-ray focusing mirror. And you know, the beam that comes out of the undulator enters the monochromator approximately maybe 4 by 4 millimeters. And we want to squash that down to maybe 25 by 25 microns. So that's about 100 to 200-fold decrease in the size of the spot that we want to have at the sample position. This vertical focusing mirror will basically squash that beam down in the vertical direction. And our focusing that we get horizontally happens actually in the monochromator through a bent crystal. And then after it goes out, it goes out of the tank and then in through that wall, which is where the samples so this is the experimental station, and there's the other side of the wall that we were just on, goes through this tank that actually doesn't have anything in it right now, and then enters some more beam conditioning elements on our goniometer system. And if we get a close-up view here, so sample is going to be mounted right here. This device that I'm pointing to here is a cryo stream that flows liquid nitrogen vapor over the crystal to keep it cold. That orange nozzle there is basically just a vacuum that sucks up the vapor and has exit kind of behind the goniometer. We've got a beam stop here that prevents the direct beam from going and hitting our detector. And then this device here is actually the goniometer that will rotate. There's a rotation stage on the back, a pair of XY stages that'll center this way, and then there's a Z stage that centers this way. So the combination of all three of those things will allow you to center your crystal on the X-ray. And we have our detector right there, which is on a stage so that you can move this forward and backward, depending on the resolution of the crystals that you have. We have a sample mounting robot. The doer, so our samples that are in pucks, like this, go into the liquid nitrogen tank. And then from outside, we can select whatever sample that we want with the robot. And that will automatically mount it on. So Vivian's going to go find the pucks that we need. And we can have a, does anybody have any questions about?
I was going to, do you have any questions about the setup, the beam? You mentioned that the beam is what is the size of your beam, Kevin? Again, I missed that piece. It's not as small as FMX, correct?
Right. It's about 25 by 25 microns.
Mm-hmm. So you need a relatively size. Too small of a crystal may not be appropriate for your beam.
Yeah.
Mm-hmm.
Yeah, I think so. Thanks.
You found them?
No, not yet.
Kevin, I had a question.
Yeah.
How long, when you get beam time, do you run 24 hours? Like if our school was to put in, or the through the B&L bag they put in for time, does that run 24 hours a day and you just put experiment after experiment through and then we get the data back?
Yeah, so in principle, you could run 24 hours. The facility does run 24 hours. We have some reliability issues, so we don't run 24 hours. But kind of once we get those things sorted out, yeah, you could run all night if you wanted to.
So really, if you loaded up your doer and the robot was programmed, it could take a ton of samples in a short amount of time, right?
Yeah, yeah.
But you still, Kevin, you still need to do some manual. You have to do even the overnight. You still need to do some visualization of what your crystal is, right? You still have to.
Well, so.
Or that's going to change.
Some of this depends. I mean,
mm-hmm.
if you have some crystals that you're very familiar with and you know how they perform. For instance, if you were doing drug development work, and a lot of pharmaceutical companies do this,
mm-hmm.
and they're working with the same crystals over and over again, soaking different compounds into it, so they know exactly what they need to do for these crystals. And so they can basically program the robot to just automatically collect these things with preset collection parameters and just let it go overnight.
Understood.
I mean, that works. Can work very well.
Understood. Any other question is a question from how big is a micron?
So a micron is 1/1000th of a millimeter, which I don't know if that
answers your question.
Answers your question.
I think it might have. So while Vivian look for the other samples, feel free to, if you have any questions. And so we're in the summer cycle right now, right, Kevin? And so that cycle will run into mid-August.
Yeah, I think August 11th, I think is when the shutdown happens. And then that's the shutdowns through August and beginning of September.
He said yes, that answered the question, Kevin. So when a user comes, a user have in shifts. So we have 8-hour shifts. Is that correct, Kevin? Am I having this right? So we do 8 hours request 1 or 2 shifts, depending on how many samples they have. And each shift is usually about 8 hours.
Yeah, that's how they think about things here in 8-hour blocks. So when you're looking at your proposal and they're asking you how many shifts you want, it's really how many 8-hour blocks. And for instance, down the hall at AMX and FMX, they'll typically only schedule you in an 8-hour block.
So that's something to consider.
Yeah, unless there's extenuating circumstances, you need more time or less time. But here I try to be a little bit more flexible with the scheduling. If you need 4 hours, that's not a problem. If you need 10 hours, that's not really.
And with the sample, in this being at least different from the first light source, the sample collection is a little faster in this, right? You can go through because of the robot, the way it's automated. In some ways, you can go through more samples in that time versus the days when you have to go in and put your samples in and out manually.
Yeah, I mean, the hotter beam that you can have here versus the old light source significantly helps. The better detectors that we have these days significantly helps with that. And certainly the robot significantly helps because going in and out of the station takes time. It's just, I mean, I used to do consulting for people when I was in Chicago. I mean, I'd take the night shift, the 9 p.m. to 9 a.m. shift, doing a data collection. The beamline didn't have a robot, so at 3 in the morning, trying to mount samples is a little challenging, especially when you already put down 2 liters of Mountain Dew to try to stay awake. And now you're all jittery.
Yeah.
Okay. So.
Okay.
So we're just going to put anything in, I think.
So, Kevin, there's a question in the chat that other than cold temperature protection, what other safety practices are needed?
Yeah, so if we're pouring out the liquid nitrogen, so we have these thermal gloves that you need to be wearing for that. We have these larger doers, you know, lab coats and various things of that nature. I should be wearing some of these things.
And Tracy, when we also do beamline training when we are on site and how to operate the hatch and the end stations. So that's part of the training that users go through.
Yeah, they're, and I think justifiably so, extremely intolerant of injuries and accidents here. So.
Kevin, there's another question on the chat. When the robot is collecting samples, exactly what is it doing? I'm a little confused on its purpose.
Sure. So what the robot does, so this piece here will go down through that hole in the dewar, and it'll pick up a sample, carry it over here, and stick it on the rotation stage, and then come back and wait down in the dewar so the end of it stays cold. So really all it's doing is it's trying to move the samples from the dewar and keep them cold and put them on the goniometer stage where they can remain cold because of the cryo stream. And that's really the entire function of what that is supposed to do. It relieves you from having to go in and do that yourself. And it also gives you the ability to do this in an automated fashion. It's a convenience that I think everybody expects nowadays to have at a beam line. You've got a robot that will do your sample.
Thank you, Kevin.
So now we are going to interlock the hatch. And there is Dieter. And once this sign ends, so this means the area is interlocked and that we could go in. We turn on the beam. So this means that when we open the shutter just in front of the sample, that it will be irradiated. Kevin is just checking again the beam position. And then we will need to bring the beam to the crystal. So in order to get into the hatch, you have to close the shutter in the front end that's in the behind the wall. And we put something in the beam pass that fluoresces so that we know the exact beam position. And here we go interlocking it again. Peter, say hello. Peter helped building this beam line. So he's kind of the father.
Okay, so we're pretty much ready to go to start doing data collection.
Okay. So do you, Bolen and Halloran, let me remove the spotlight here. Bolen and Halloran, are you, so they're going to be PN in, I don't know who is starting first. And then Bolen, who will be doing, do we doing the screen share?
Yeah, I'll share my screen.
Mm-hmm.
I'm in already. I'm connected. So I have the blue ice image. I'll show you what I have.
Mm-hmm.
Screen. Let me just share.
And then, and so in the remote access, something that if you, if you decide to join the collaboration, the program, you will request a BNL account, you will request a VPN access because this is inside the BNL wall. My understanding is they're trying to make this a little simpler. I don't know the details of that, but as of now, you have to connect yourself inside the BNL wall to have access to the remote desktop machine. So I'm gonna let Bolen and Halloran go through the process with Kevin.
First off, can you see my screen? Am I sharing the right screen?
You are sharing the right screen. I can see the no machine, and I can see
you see all the tabs: Hutch, collect, sample. Is there a blue square?
I do, and I see the resolution prediction. There's a schematic of the mesh of the.
Perfect. Okay, great, excellent. Okay, so being that it's been about 4 months since we last did a beam time collection here, I'm going to ask Kevin to just give us a quick walkthrough, so this way everyone kind of sees what we're doing, also to refresh my memory.
Sure. So there's, as I mentioned in my little walkthrough, we've got 3 monitors that you
right.
And so this is the data collection monitor. So can you switch to either of the other 2?
Right, and just remind me how to do that.
It's control option 1.
Control Alt 1. Yep. Okay. There we go.
Okay. So on this window, we've got set up this program called ADXV, where you can look at your fraction images. And if you go to the preferred desktop,
so let's see.
I think it's a control something.
3? Yeah, there we go.
3. Do 2.
Okay. Yeah, there we go.
Okay, so basically all you need to kind of be concerned about on this page is we've got a web camera, so you can see what's happening, and I can if we do that, then that amount of sample, and we can see what's going on.
Okay.
So if we go back to the blue ice window,
okay.
Okay, so the collect panel is where you'll do your data collection. And so we've got a number of tabs set up, which you can select on the very far right there. So the number 1 tab, we have set up to do your full data collection. And then the number 2 tab will collect 3 images at 0 degrees. And the number 3 tab will collect 3 images at 90 degrees, which you can use for screening and kind of get an idea of how your crystal looks and make a decision if you do or do not want to collect on this sample. Now, if you go to the sample tab, so this is where you can choose whatever sample that you would like to mount in the robot, and there's this graphical representation of the puck. You can just click on whichever sample that you want,
Okay.
and tell it to mount that one, and I see that it thinks something's mounted, which is, let me clear that.
Okay.
So your puck is in position A.
Okay.
You can go ahead and select whichever sample you'd like.
Okay, we'll try number 1.
Yep, and then hit mount. And then go to that's desktop 2 or 3 or something with the web camera.
There we go.
Okay, so you can see the robot's now gone down into the dewar. It's soaking. And it'll stay there for some amount of time to let it cool down.
What's pretty impressive with this is I'm controlling the lab from my dining room in my house right now, which is pretty amazing that we could do this. While that's cooling down, when we do this with students, we usually try to schedule the beam time either after school or later on in the day, because we found that doing this during the course of the school day, this is too much interruption with bells and kids changing classes and whatnot, and trying to get substitute coverage. So we usually do this later on in the day, and what that usually does is frees us up so that more teachers can get involved in the process. And the idea is that eventually all the teachers in the collaboration would get a turn at running this and getting a chance to what we call drive the beam in doing this data collection. All right, is that sample mounted? We're good? Oh, here it goes.
Okay, so you can go back to your blue ice window.
Okay.
Okay, so typically so you're in the sample low tab.
Mm-hmm.
The only thing you need to really do here is just, you can point and click on wherever you want to center. Yep.
Okay.
And then rotate 90 degrees. And then you can move to the sample high tab. Oh, I want to, sorry, go back to click the low.
Okay.
You want the sample high tab, which is next to the sample low tab.
Oh, here we go. Yep. There we go. And do we have?
Kevin, can you say why the rotation is important?
Sure. So if you want to rotate or center something that's on a rotation axis, then get it centered in one direction. It may not, when you flip it over, as you saw in that, it may not be centered in the other direction, but it'll swing up. So you need to then bring that one down so that when you rotate it, it's all on the same axis, which is something sometimes people forget to do. They think that they've got it in one orientation, and then when they think they've got it centered, when they really don't.
Right. So right now what we're looking at is, this is the loop. I don't know how good your resolution is on the screens that you guys have at home, but this is the loop. And in here we have some items here. We're not sure if these are crystals or not. We're not exactly flush. So we would be able to use this +10 and -10 to try to get this to be a little more oriented so that we're looking at it straight on. And then we can kind of see a couple of things here. I don't know if there's a crystal here. It looks like there might be a crystal here. This is OEP4, right? So this might be, actually, I have the spreadsheet.
It's not OEP4, it's OEP1.
Oh, this is OEP1? Okay.
Do you have the spreadsheet for it?
I was looking at the spreadsheet before. Let me pull this up. OEP. No, this was, I have a spreadsheet with 405, 108, 109, 110 on it. This is one? Okay. So we have to pull up a different spreadsheet for that.
So we may have 109.
Okay. 109 is my AB and my PTB. So there's a couple of different ones in there. Okay.
The 109?
Yeah.
And these two, go ahead, Vivian.
Good.
Because I couldn't find those pucks.
Okay. So what do we have loaded in? We have one.
So we just have one. We can load the others if that is.
Okay, yeah. I think this looks like this is a my PTB because it's got this very narrow crystal right in there. So
for the participant, there are two proteins that the collaboration was working on there. You want to tell them a little bit, Bolin?
Sure. The two proteins we're looking at are tRNA methyltransferases, and they're from two different species. So one of these, and basically what these proteins do is they're involved in the methylation of tRNA during protein translation. And so the MyAB comes from Mycobacterium abscessus, and the MyPTB comes from Mycobacterium paratuberculosis subspecies avium. So they're from two different species of bacteria. The MyAB proteins form these really nice big crystals. They look almost like a brick. And then the MyPTB forms these crystals that look like these very thin needles. And a lot of that has to do with not only the protein itself, but also the conditions that we grew these proteins in. And so in this particular image that you guys are looking at, just where this plus sign is, right above it, I don't know if you can see where my mouse is, my arrow is pointing. There seems to be a very thin, narrow crystal right in there. And so that might indeed be I'm going to just kind of move it a bit to get right on there. So that might be one of the PTB crystals. And so just after looking at these for a bunch of times, we kind of get the idea of what our crystals look like. And so this is a real thin, narrow one. So we'll try to collect on this one. If that doesn't work, we'll look around in the puck and see if we can find anything a little bit bigger. And then try to also see if we can pull up the spreadsheet. What we do is we make a spreadsheet that contains all the information about each crystal and each sample that goes in each of these pucks. Each puck can hold 16 different samples. And so sometimes what we'll do is we'll fill half a puck with one protein and half with another. Or we'll even do it with proteins that have different types of conditions. Sometimes we'll add different ligands to them, different compounds that we want to mix the protein with. And then sometimes we'll cryogenically protect the proteins using ethylene glycol or glycerol. And sometimes we don't, depending upon the structure of the protein and what it looks like. So in this case, this is OEP number 1. So we're going to have to go back to a spreadsheet and just double check what this came from. This might have been a puck left over from another beam time. So we're going to check that one out. I don't know, John, if you're on and Alade, if you want to take a look, I think this one might be from the AMX back in February of this year, because this is the NYX data from March. So if we could just take a quick peek at that and confirm. And then in the meantime, Kevin, we'll try to shoot this and see if we can collect anything on this one, if that's okay.
I think you can collect if you feel
okay.
You're ready. I think Kevin is talking with Martin right now.
Okay. So Kevin, we're going to try to collect on this one. It's a real thin crystal. I centered it on where I think I can see the crystal here. And then I need to rotate 90, correct?
You can, yeah, rotate 90.
Okay, I'm going to go plus 90. And again, we're just a little bit off, so I need to click to bring this up a bit, correct?
Yeah.
Okay. And I'll go back 90.
Okay, so
Yep, we're there.
So Bowen, you
Yep.
can actually see a little bit out. It's sticking out.
Oh, I see another one up here. Yep, at the top.
yeah, so
Yeah.
that's
Yeah.
where I think you're probably
Yeah. So let me move that up. And then we'll rotate. Yeah. Does it look like we're right on it? Yeah, the crystal's actually right up here too, sticking right out.
You're right on the end of it.
Yeah.
So yeah, you could go in, yeah, right there.
Right here? Okay. Oh yeah, okay. So do we look good, guys?
Yeah, so I think you need to, let me just pop up.
Go ahead. Now, usually the first one or two collections we do, there's usually a lot of discussion or, making sure it's oriented the correct way. And you'll see that throughout the whole data collection, especially with us because we're teachers and we're not beamline scientists, there's a lot of Q&A that goes on, which is great. And Kevin and Vivian are so super helpful with this, making sure we understand it. Especially, again, since the last time we did this was in March, we're now in the end of June. So between that and having, the COVID stuff going on all year, we forget things sometimes. Okay.
So you can go ahead to the collect window.
Okay.
And yeah, you could go to just number 2 and 3 and fill those out.
Okay. So we'll do 2 first, right? Okay.
Sure.
So just help me out again with this. So this is important with the naming. We want to make sure we have everything set the right way. So what are we going to call this?
So for the screening, you could just, because you're just doing the screening shots, you can leave those just
Okay.
at screen. But probably the more important thing is you need to make below that a subdirectory at the end there.
Okay.
Put your samples in.
Okay. So this is OEP 1.
So you need to put a backslash.
Okay. Okay. And then we have OEP 1. The backslash OEP 1. Is that sufficient? That's good enough?
And this is pin 1. So
Yep.
you could make do another
yeah.
subdirectory like pin 1.
There we go.
And then you can do another subdirectory and call it screening.
Okay.
Okay.
All right. And I'm on tab 2 for that, correct?
Yep. And
Okay.
tab 3, you can just, well, for some reason it won't copy and paste.
Okay.
So I'll tell you, so go to tab 3 and just push the delete button.
Okay.
delete button above the screen.
Yep.
Okay, then go back and push the asterisk that's under Tab2.
Okay.
Okay, so that'll just duplicate Tab2.
Oh, great. Okay.
So then all you need to do is go down where it says frame and phi. So change the starting phi from 0 to 90.
Okay, from 0 to 90. Okay. Didn't take it. Okay.
Okay. And so, yeah, I think you're good to go.
Okay.
Then you can go back up to tab 2 and push collect.
Okay, this is from 0 to 0.75 on tab 2. Do we need to change that or no?
No, that's fine. That's
fine.
zero
Okay.
selection.
Okay, and then hit collect.
Yep.
Okay.
Robert, and,
Yes.
and when what after the data is collected, can you review again like what some of the stuff means? Give a sense to the participants, you know, an overview of the steps and what do they mean?
Yeah.
Selecting X one number versus the other.
So in terms of what we were just doing here up on the top, what we were setting up was a directory because each puck has its own, has 16 samples and each sample is unique or it may be unique. And so what we're doing here is when we collect, we'll have this put into the directory. So we know that, okay, this is what we collected on pin number 1 in puck 1. And then we'll have pin number 2, puck 1, pin number 3, puck 1, and so on. Down here, what we were doing is we were just changing our start and end because we were collecting at 90 degrees. So we were doing a 90-degree rotation on the pin. And if I go back, let's see, there's 1. This is eventually going to show us the diffraction data that we get once we collect it. Did it collect already, Kevin, or not yet?
Yeah, so push the list.
Okay.
Click that directory once.
Okay.
Once. And that once. And there's
Okay.
your images. So just
Okay.
select one of them and click load. And doesn't look like there's any diffraction.
Okay.
Looks like a block of ice.
Yeah.
You see the ring? You can show that this is what the eyes look like.
Yeah. So this is bad diffraction. So right here, you can see that you have this heavy line here. That usually indicates an ice ring, which means we have ice in there. And then sometimes you get a second one here that shows as well. If we had really good diffraction, you would see beautiful dots showing up here. You'd see all these dark dots, and you'd see a very specific pattern that would show. So our first shot is epic fail. So we're going to try another pin. Were we able to determine what protein we had in this one?
Yes, I did look. It looks like it's MTHFR.
Oh, okay. Okay, and that's all of these? 2, 3, 4, 5?
We're going to sneak in the end station and look at the pucks, and maybe there's a different puck that we can also load.
Okay.
So
Excellent. So a couple of questions. Does prolonged cryo protection damage the crystal? That was from Jim. So the cryo protectant, again, a lady could jump in too. The cryo protectant is what prevents the crystal from being damaged by ice expansion, right?
It protects them from the beam. It's like a sunscreen, and also prevents crystal ice formation during the cryo time. It depends the cryo. So some proteins, depending what kind of cryo you use and the concentration of that, it can damage the protein while you're fishing it. So what we try to do is, we're not sure if it does that or not, we will collect samples without the cryo protection, and we will collect samples with cryo protection and see it's a difference in diffraction, that information that we get. I don't think it's the prolonged cryoprotection damage the crystals. I think it's just the type of cryo that you use is important. And that in some crystals, protein crystals are more sensitive to some type of cryoprotectants than others, than others.
We also noticed that when we were working with the Maya PTB, that it actually wasn't doing too well with the cryoprotectant, right? And so for the proteins that my students worked on, we noticed that the cryoprotectant was interfering with the crystal structure.
Yeah. So go to Tracy's question. So we have eyes, and sometimes we do get eyes. It's just that for this particular case, there was no diffraction. So I will think about it more like you have an ice cube there. So when you have no diffraction and diffraction, we just simply leave that crystal out and go to another crystal to see if we can obtain diffraction data. Mike, sometimes when you do this, not all your crystals will diffract well, and not all the crystals will diffract the same. So that's why you have many crystals of the same protein, because until you take it to the machine, you don't know what you get. So in this case, we just simply had a crystal, no diffraction, and the ice that we see is just probably from the cryopreservation.
So you can go ahead and mount another sample.
Okay. From the same puck or?
Yeah.
Okay.
That's why crystallization I think it's an act of perseverance. Crystallographers are people with a lot of perseverance.
So we're going to try to mount number 2. We'll see what this is. And so this is MTHFR. This is OEP1.
Yes.
Okay. Okay, and we'll switch back just so you can see what's going on. Here's the robot, again, going in. And now it put the other sample back. Now it's taken the current sample.
So that just mounted your new sample.
Mounted the new one, right? Yep. Okay. So let me go back to this. Okay, and so we are going to go to sample low. Okay. And then we'll go sample high.
Rotate 90.
Oh, rotate. Yep. Oh, wow.
Oh, so this is opaque. That's going to be difficult to see anything, I think.
Right.
You can kind of see it.
Yeah, a little bit. Is that reflection or is it? Yeah. I don't know if that's.
Yeah, I don't know. You could.
Yeah.
If you want to try mounting another sample.
Yeah, let's just do that. Okay. All right. I just click on it and just click mount, correct?
Yes.
Okay. Let's try 3. Usually we blame the not so hot samples on me.
Remember when you do this in crystallization, like I said, you do a lot of samples, not because when you do the cryo and all that process, until you actually go to the beam, you do not really know the state of your samples.
True, you don't. Yeah.
And so,
once you've done that cryo protectant and you put it in that puck, you have no idea what it looks like until it comes out of the puck and goes into the camera. Let's see. Let's go to. All right. Let's see what we have. So it's a lot of it's real science. It's true trial and error. And sometimes, depending upon what happens with the pins too, sometimes you have a pin that Ooh, looks like there's something in there. Right around here and here. Let's see.
So, Bolan, you're going on high, right?
I'm on high now.
To walk the steps with the participants that they have.
Yes, sorry. Yep.
Okay.
So now we're on sample high, and we have some nice crystals here. Can everyone see those? There's one here. There's one right here on the plus sign. So we have a couple of nice crystals here. We're going to try to maybe get down here a little bit.
And I hope you can see the sense of the loop, you know, with this drop, really.
Yeah. So the loop is right here around the outside. We have a little bit of reflection on the bottom and on the upper right-hand side here. And there are actually three crystals. There's one here. Can you guys see my mouse? I don't know if you can see my mouse.
Yeah. Yes.
Okay, there's one here. There's another one here. And then there's another smaller piece here. And then there's like a fragment over here. So I'm going to try to shoot right on top of this one here. I'm just trying to get my plus sign to be on top of that. I think we're as close as we can. And then we're going to rotate 90 degrees. Are we on it still? Can you tell, Kevin?
It's hard to say.
I'll go back again.
Yeah, go back. I mean, it seems like it's. I would just give it a try, and you know that you're going to be hitting it in one direction. So
right. Okay.
See what it looks like.
Okay. All right. So we'll try to hit that one. So then we're going to go to the collect screen, and we're going to go to tab. We're on tab 2 right now.
Yeah. So you hit reset.
Okay. Let's see. Where's reset? Oh, here it is. Okay.
And you just need to change the pin for pin 3, I think.
I think pin 3. Yep. Okay. And then we're going to do the same for tab 3, correct?
Yes.
Okay. We're going to do pin 3.
Reset. Push reset.
Oh. So it's pin 3. Oh, no. Jumped on me. I don't know why. There we it doesn't like what I'm hitting. I don't know why.
I think it's your mouse is the cursor's moving out of that. I can do it really quick.
There we go. Okay. All right. And so those are all set. 90, 97.5. We're good. Okay. And then we'll hit collect.
Go back to 3. So did you delete the G at the end of the screening?
Probably.
Okay. There you go.
Yep. All right. Thanks for catching that. All right. Okay. So we're all good for these two, and then we can hit collect.
Yes.
Okay. And so by hitting collect now, what we're doing is we're collecting data. So we're now allowing the X-rays to hit the crystal and hopefully get some kind of diffraction pattern out of it.
So you'll need to go to the pin 3 directory.
Okay.
So you can either click, yeah.
Oh, you just go right here.
Yeah, you can just type up there pin 3.
Okay, and then hit list.
Okay.
All right. And then hit load.
Yep.
Okay, we got some things here. But Vivian, just say that we can't hear you. It's a little, yep. Yes, we do have some diffraction here. Okay, you can see some dots here. This, we get these little streaks which we see this a lot with those, I think if I remember this, with those needle-like crystals, that's one of the characteristics that we tend to see with this.
If you middle click on top of those streaks, or right click, move that, there you go. So it's moving back. So you can actually then see all those spots.
Okay.
Kevin, can you tell us, to the people that are not familiar, what do the spots means?
So the spots are, so if you want to consider that, so the spots are the result of the diffraction of the X-rays through the lattice. So you'll get a predictable pattern of spots. Let me just make I'll push the list button again.
Okay. Okay.
Where your other samples went, screening images went.
Oh, this is my PTB. Okay. All right. Well, there we go. Big ice ring. There we go.
Did something happen with Kevin?
Yeah, Kevin's just making some adjustments so we can see we can visualize this a little bit better. So you can see the diffraction pattern a little bit better this way. And something was up. I wasn't clicking on something.
And just to let people know, when we have new, particularly if you have protein that you don't know much about it, we will collect this data and analyze it because you build data from one to the other. Go ahead, Kevin, sorry.
So looking at this, you can take the pointer on the ADX feed, you can move it around onto various spots, and it will tell you what resolution that you're getting on those. So Robert, you can go ahead and do that.
Okay. Okay, what am I clicking on? I'm sorry.
So if you hover your mouse pointer over that image, so in the top left of that image, it says there's an I and a colon and then some numbers. So wherever the pointer is, it says 4.56A. So that's your 4.56 angstrom resolution.
Okay.
That image. So you can look at these images and kind of get an idea about what resolution that you're getting.
Right.
Okay. In your testing.
Yeah. So we have a couple of these are going to about 3.2, 3.1 angstroms. That's really getting far out here. But you can kind of see over here, there's a little bit, if you guys look, if you can see in this smaller magnified box right here. Can I make this bigger, Kevin, to show people? Yeah. So in this area here, can everyone see the screen? Anyone not see it? There's a little bit of a pattern here. You can kind of see that there's a streaky line here, one here. There's kind of like an open space here, and then it's sort of repeats itself here a little bit. And you can kind of follow these streaks, and that gives you a sense of the diffraction that's going on. And also you can kind of see there's like an arc here. Like there's a couple of dots here, there are a few here, a couple here, 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 and here. And if you follow this around, there's like a little bit of a circle this way. This forms more of a complete circle. So there's a little bit of a pattern. And Vivian and Kevin, if you guys, you know, obviously you're the experts on this, you can chime in. But that's kind of what we're looking for, is we're looking to see, do we have some kind of organized pattern there? And then Vivian and Kevin usually will, you know, assist us with saying, yeah, that's good. We should definitely collect data on that.
Yeah. So there's no diffraction in the 90 degree.
Okay.
So what that means, if you get diffraction in one direction and you don't get diffraction in the other direction, that means that you're not centered. So if we were going to collect data on this, then we would have to go back to the 90-degree orientation and try to do a better job of centering that to get the crystal into the beam.
Okay.
Assuming you want to collect on this, or want to go to the next sample, I'll leave that up to you.
What do we think, Aleda? Just thinking about in terms of timing and everything too.
Muted. I was muted.
Okay.
So we are at 10. Maybe, so two things that I think we can do. We can try to see, to show them that the whole process, meaning that the whole full data collection at some point. And then I would like to, if we can go back stepwise and to kind of review what the steps are, because data collection, the participants are not going to be experts in data collection. It takes some time and practice, but I guess I give you a flavor of what that process looked like and the full data collection. I don't know whether you want to do another sample or not. Yes, Vivian?
I think we should collect on this sample.
Okay.
It has nice diffraction, even though it's not up to such a high resolution.
Okay.
And perhaps, I don't remember exactly what we have on the agenda still today.
It's just data. This is the agenda for today.
So I think we should kind of do some screening, maybe a couple of other samples. We only have my PTB on this cup.
Okay.
It is one of the very first ones that were crystallized.
Okay.
From what I could infer. We have other pucks in there, but I cannot find the spreadsheet. I did find the spreadsheet for this one.
Okay. What are the other two pucks that are in there?
I'm looking for pucks NSLS2 MX 101, 102, 103, 104.
Okay. Check those. Okay. So Kevin, if we want to collect on this, we need to go back and just make sure we have the 90-degree set correctly.
Yeah. So this is the 90-degree view.
Okay.
So let me just do something really quick.
Okay.
And Bowman, before today's morning session is over, I would like to do a quick overview on the process, so that the participant had a flavor in the how-to, right? They're not the how-to piece. Because it's recorded, they can probably use that as a reference starting point.
Exactly.
If and when they do collect data in a remote setup.
Right. So while Kevin's doing this, so just to recap, so yesterday participants got to see what a wet lab demo of crystallization, of setting up the crystals in the tray. And did they get to see how we harvest crystals with the pin?
Yes.
Okay. So then those harvested crystals that are in those pins, they go into that puck, they get protected in liquid nitrogen, and then they get brought over to the light source. And then those pucks were loaded, as Kevin showed us, into that large container called the dewar. And what we're doing now is going through each sample. And what you do is you screen. The first step is to make sure that you actually get diffraction. Like, is there anything showing when you shoot the crystal with the X-ray? And if you have a decent enough pattern, then you say, okay, this looks good. We can collect on this. And the idea is that when you do the data collection, you're going to collect a lot more information from the crystal. Basically, what we're going to do is take a lot more pictures. Right now, we just took 3 shots of it at different angles to see that we actually had diffraction. Now what we're going to do is go back and collect hundreds of images of this crystal as we rotate it through the X-ray beam. It's kind of like taking a picture of a person from the front, and then we turn that person 90 degrees and take a picture of them from the side. Well, you're only getting two pictures, what they look like from the front and from the side. But now what we're going to do is take that person and take, you know, a bunch of blast pictures all at once, and rotate that person a degree at a time, basically, so that you get the complete picture of what that person looks like. And that's basically what we're doing with the crystal, is we're going to take a shot pretty much at each degree as we're turning it, so we can get the complete picture of what the crystal looks like. And then that diffraction pattern, you know, if that diffraction looks good, then eventually the next step is to take that diffraction data, feed that into a couple of different programs that will allow us to convert that into a three-dimensional structure of the protein, so we can actually see what it looks like.
So Bolin, when you collect the data the next data collection, can you do it stepwise?
Yes. Yep. And what's neat with this too is with the data collection, you can actually see the changes in the diffraction. It's almost like a, I like the way it looks. It's like a stop action kind of thing, where you can actually see the diffraction as it's rolling through. It almost looks like a movie. But Kevin's just getting us set to make sure that we're good for our angles, and then we can go ahead and actually collect data on it. And again, this part here is very technical, where we're trying to align the crystal precisely, making sure that we're getting a good piece of diffraction at one angle, and then when we rotate it 90 degrees, we're getting diffraction the other way. And basically what happened is I didn't have the crystal set exactly correct. So at one angle, at one face, we were collecting data, and then when we rotated it, the beam was missing the crystal. So basically what we're trying to do is make sure we have the crystal aligned in the beam when you rotate it in two directions. So we're making sure we're aligned where it's facing us flat, as you guys can see in the screen. And then when Kevin rotates the pin on edge, we want to make sure that the beam is actually hitting a crystal and it's not just going through either thin air or just, you know, whatever cryo protectant is in there. So this sometimes becomes tedious, and this sometimes takes a little bit of time, but you want to make sure that you're precisely hitting the crystal. And the challenge with these two is these are very small needle-like crystals. So when you rotate it, there's a good chance that we're missing the crystal. And so that's why we have the experts who can really get a good glimpse of it and make sure we're on it. With a larger crystal, it's bigger, you have a bigger target, so it's easier to align it, and there's a better chance that you're going to get the X-ray to hit it when you're turning it and rotating it.
But then you are not irradiating always the same spot if you don't take care about the alignment.
Right,
either.
right.
So crystals may be not very well ordered.
Mm-hmm.
But this is something for some other time. And then it becomes very difficult to actually extract the data from your diffraction pattern.
Right.
So alignment is critical, no matter how big your crystal or how small your beam.
While we're waiting for Kevin to set up, there's a question, Rob, how much of this process are the students involved in?
All right. All of it. Basically, you know, the goal is that the students are going to be creating the, you know, working on the conditions to get the crystals growing, grow the crystals, harvest the crystals, put the crystals in pucks. And then in this piece here with the data collection, we had students collecting data at the last beam time. And that's the piece where students need to be, they need to have access as remote users. And that's why all the students in the fall will go through this process where they're going to do the same training that everybody else did. They're going to have to go through the same training process so that they can then be remote users. The students are treated as if they themselves were scientists. So they will have the same access that we do as teachers. They'll have the same involvement that we do as teachers. Prior to COVID, we would bring students to the beam, and students would go through rotations, and they would actually sit at the computers. They would go through the same training process that a scientist that would be visiting the lab, and they actually would quote unquote drive the beam. So students will do all of this. Of course, under the close direction of teachers and the scientists, but students do have a role in doing all of this. And then afterwards, the students are going to do all the data analysis too, which actually takes the longest. This is the part that is the most fun because you're collecting data, you're looking at your crystals, you're looking at how good they are. And then the piece after this is looking at all this data and trying to figure out, you know, which data set gives us a good structure. Did that answer your question, Christine? Okay. Yep. Okay.
So we're going to go back and collect from that same sample?
Yeah, I think Kevin was just setting that up. Go ahead.
So we've had something that happens when you go to the synchrotron, which is that they dump the beam.
Oh.
Can you let people know what that means?
What that means is they've lost the current in the storage ring, and so they're not able to supply X-rays. And so, Robert, can you go to the ADXV window?
Yep. Wait.
Did they give you an ATA, Kevin?
Wait, I have to go on here.
Oh, it just quite literally happened. So
Okay.
then what happens is, like, I collected some images, and there's nothing on them, as you can see.
Okay.
Indicates that you've got no X-rays. So I really, it usually takes them, in a best case scenario, probably half an hour to get this going again. So I do have some data that are collected. If you want to, I can just show you on the ADXV window if you want to just kind of see what like a full data collection looks like. Okay.
Thank you, Kevin. And while you get ready, there's a question from Allison's making a comment. We, as teachers, you have the opportunity to do this without your students. I said, yes, we do. We tend to have an opportunity to find time to do a training session for teachers only, so the teachers can become more more proficient, and not just a proficiency, but also getting comfortable with how to use the tools and the commands before you go ahead and do it with the students. So it's not like you just go in and we give you VPN access and say, go and figure this out.
Yeah.
It doesn't work that way.
So what I put up on the window there is a test crystal that I collected some data on for somebody. This is a trypsin.
Okay.
And it's used as a test because it just diffracts remarkably well. And I think I don't know what this, I got this down to be, probably you can get down to 1.3 angstroms or something like that. So, Robert, if you can push the double arrow strike button.
Yep.
Yeah, push that one. So that will just stream through all of these as if it were a movie, and you can see how the pattern, diffraction pattern changes as the crystal rotates through the X-ray beam. And so after you get your data set like this, one of the things that you'll need to do, and I'll talk about a little bit in more detail tomorrow, is you need to take another piece of software and reduce your data down to some format that you can do something with it. And what this involves is basically predicting where all of these individual spots are and adding up the intensity of the pixels in those spots, and then combining them all together into one large file that you can then calculate electron density from. And let me jump in there real quickly.
Well, Kevin, come back. There was a question, a comment, and sorry.
Oh, so I was just going to show. So I zoomed in really, really tight on one of these pixels, and so you can see there's the numerical value for the intensity in each one of those pixels. So the software will try to draw a box around each of these things, and then it'll called integrating, and it'll just basically add up the sum of all of those pixels inside this box that's drawn around it. And then it'll do another mathematical treatment with a slightly larger box around that to estimate what the background is, and it'll subtract the background out of the intensities that it's got, and it'll write that into the file that you can then do something with. So this business it's very math intensive, and fortunately for people like me that are not math geniuses, there's a lot of people that like doing this for a living and are very happy to write software for people to use to do all this, instead of it being the good old days where you had to write your own programs to do all these things in Fortran. So you had to know all the math behind, how does the diffraction work? How do you predict where spots are going to be? How do you do scaling for spots? How do you calculate electron density? So the software products that are available now are kind of opened up this to a lot more people to do this without having to know the gory details of how this actually works.
There are a couple of questions that came up in the chat. So John was addressing them, and I'll try to also speak to it as well. One of the questions people had was the proteins. Where do we get them from? How pure do they have to be? Are most students looking at proteins that are easily purified? And like John had put in a link there, it's from this place called Seattle Structural Genomics Center for Infectious Diseases. It's a really long name with a long acronym. Basically, they are a facility that purifies the proteins for us, for anyone. And you can obtain those proteins for free. The only thing we pay for is shipping. So, I just write it off. It's a tax write-off. But basically, we get these proteins from them, and they're purified already. Some of the proteins are in the protein data bank. Some of them aren't. And even if they are in the protein data bank and they've been resolved or published already, we can still do other studies on them. We have a whole bunch of ligands that we can do studies with. So we have different compounds that we can mix these proteins with to try to see how they diffract and what does their structure look like. We can use things like magnesium, EDTA, for example. We've done studies with that. But that's really the best place for us right now to get them from. Trying to purify proteins ourselves, it's really not effective. It's very costly and time consuming, and that's a whole nother world of science. So that's where we tend to get ours right now. So fortunately for us, John, actually, I have to give John the credit for this. They started getting into these TRMD proteins, and we started to look at them as a group. And it's become a hot topic. It's become a type of protein that seems to be a big target right now for alternative drug design, because it's a prokaryotic protein. It's unique to prokaryotes. And it's something that, as we've looked at these, we actually have a few structures that are not resolved. And so, for some of us, it's been a nice thing because students are working on something that hasn't been resolved yet. And in some cases it has been, but we're doing additional studies. In some cases we're getting better structures, and in some cases we're mixing it with different types of compounds. And so it's real exciting that way. Vivian had put up here, it's important to check the protein data bank, the PDB, before starting to know what the status is on a protein. And again, the protein data bank, it's online, it's a link. Did we talk about that yesterday?
No, because
No?
I think
Okay.
we're gonna leave that for later.
Perfect. So we'll
Because
leave
we
that
were
for later.
for later.
Okay.
Because we were gonna, we can talk a little bit. I don't know if the beam is back or Kevin is done doing his thing, doing the presentation. No back, no beam back.
I don't see it. Yeah, I'm looking at, I'm on the website now. Yeah, it says case cause unknown, update to follow.
So my question is, and I know these things do happen, maybe we can just talk about some of these things, but before we go into that direction, is there a way that we kind of, because there's no beam, we can kind of recap how the process worked? Kevin, is that something that we still need beam for that? Or can we just do a walk through how the data collection happens?
Sure. Well, it's actually just very similar to the screening images. So we had it set up to just collect 3 screening images. Instead, we had it set up to collect, like 900 images. So it's, as far as the setup on it, it's very similar to doing the other data. So you're just collecting a larger contiguous wedge of data.
So basically, Kevin, in essence, what we did with the screen was take maybe 2 or 3 snapshots of the protein to make sure it diffracted. And when we're doing a collection, we're taking hundreds of images of the protein as it, basically, if the protein's like this, as we rotate it through the beam, we're hitting it with the beam at this angle. And then as we rotate it, the beam is continually reading.
Yeah, so that's like that set that I've got up here with the trypsin. There's probably well over 1,000 images.
Wow.
They're just contiguous.
Yeah, I'm just kind of scrolling through it right now. Yeah.
So I think what we're gonna, because I don't know when the beam is gonna come back, and the beam can come back in 10 minutes, or it can come back in an hour, or tomorrow.
Yeah, I just hit the play button on this just to show everyone. Yeah, this is, I mean, we're up to almost 900 images right now that this took. Yeah. So
any questions? I know that what I was hoping is that, I hope that we were able to kind of show to participants a little bit of the stepwise process and how the various windows and how the sample collection does happen. Any questions? Any things that come in your head about the data collection process? Go ahead, Adi, ask your question. You can unmute yourself if you want to. And what is the overall outcome after the data? What is the overall outcome after the data collection is completed? Like the purpose of the data completion, the data collection.
Yeah, so this gives you the basic information that you need to be able to calculate the electron density, which is what you'll use to build your model from. So the X-rays interact with electrons. They don't interact with the nucleus of the atoms. So they're diffracted by the electron clouds of the atoms. And so what you're calculating at the end is the density of the electron cloud in the crystal. And then because we know what amino acids should look like, and we know that the geometry and the angles and what's connected to what, you can fit these things inside the electron density that you've collected, and then use a program to mathematically constrain these atoms that you fit in here to the electron density that's around it. So the data that we collected is really this will determine the quality of what it is that the model that you'll have at the end. So you need to do a, as good a job as you can to collect the data and not, you could overexpose it, cause radiation damage, which will have a negative effect to your model. So that's, I hope that answers your question.
Did that give you Adi? There's another question about the work rating was used a few times yesterday and today, and what is a kind of a bit more explanation what that is.
So we're
I talked about it yesterday, and basically, remember the first slides that we saw in Nature, where we had the barriers located in front of a beach, and they had some holes in it. And when the wave front was coming in, you had only part of that wave going through that blocking, and then in making like circular waves that interfered with each other. Then we use the example of the red laser light shining on top of a grid. So a grid can be made out of any kind of material for visible light. In fact, my fingers, if I would come with a light from this point, they can act as the lines in the grating, like the spacing, depending on how much I open my fingers. So in the case of a crystal, you would have that all the atoms in the crystals, they will be acting like these lines in the grating. So they will be blocking certain parts of the space, and the X-rays will deviate from down. I don't know if I can share again.
So are you saying that the crystal is the grating material? Is that?
Yes.
Yeah, okay.
It's a grating, essentially. We don't talk about it as a grating when we talk about in crystallography, but it is. Let me share that with you.
Okay.
Can I open this?
And I think was the beam, like, I know there was a discussion about the proteins. If there's no more questions about the data collection itself, then I know there was some discussion about the protein, the acquisition of the proteins and the sources of that. And I think we can continue with that.
So remember when we talked about, so we have the laser that's pointing perpendicular to the page here, and we have diffraction. We have very thin lines in this slide, and we can see them diffracting. So we call it the first order diffraction on each side of the direct beam.
Mm-hmm.
Make sense?
Yeah, yeah.
Okay.
Yeah.
So then we talked about crystals. We talked about the sodium chloride crystals.
Mm-hmm.
And if we would go and look at a sodium chloride crystal in very with very, very big detail, we would say that we would see that they arrange themselves in a cubic shape. And that cubic shape is shown when we grow salt crystals from solution, like we have here. And so what I did here, I took one of these planes and I mounted it here. So you can see, okay, this is really macroscopically, but salt crystals, it's made out of many, infinite numbers of tiny little sodium chloride cubic crystals.
Mm-hmm.
And each one of them will have this kind of distribution pattern for the sodium and the chloride atoms. You see there's a lot of space in between them, but each diffraction spot that we are seeing on the diffraction pattern is a result from the interaction of the X-ray light with these individual atoms, and give us a representation of the distance between these atoms. So as somebody asked, what is the result that we get out of the full data collection and of the data analysis is actually a representation of the electron cloud around the atom position. The higher the resolution, the more in more detail I can define this cloud around the atom. And that one is represented here by this mesh, this electron cloud. Makes sense?
Yeah, I'm sorry, I have another question. So is the X-ray diffracting from the interaction with the electrons of the atom or with the nucleus? The electrons? Okay. Okay, thank you.
Like, for example, visible light interacts with us, and so we can see each other, we can see the objects.
Okay.
Sound waves, they interact more with the building, right? And
right.
So we can we can hear sound. We cannot actually hear if we would be in the vacuum.
Got it. Thank you.
Any questions about the data, what you saw in the data collection process? And again, as we mentioned, it's not like we just say, you come and collect data and we dump you there and you kind of, it's a process. So we find time to have our teachers be comfortable and in the data collection process. It takes time. So one thing that you have to be mindful is that this is also, it doesn't happen right away. The more you do it, the more comfortable you are. Then it starts to become a second nature. That takes time. So I encourage teachers to get the hang of it first, so that they can work with students and getting the students, supporting the students in the data collection, because the students graduate and kind of move, but the teachers will be the ones that stay behind. And so it's something that it does take time. It does take time. So my suggestion is that you give yourself some time when you start our data collection process. And it's real life. Sometimes things work and sometimes things just don't work. So we just collect more data and make more crystals. Yes.
A favor, would everybody be comfortable to turn on their cameras so they can make a group picture that will be used basically for Spark and for NYX reporting?
I did take a little, when data collection was happening, I did take a little bit of that too. Do you want me to take it, Vivian, of everybody?
I'm going to take everybody. So everybody tell us when are we good?
If you're comfortable turning your camera, I appreciate it. If you're not, then you put your...
That's fine.
All right.
I need two because we are many. Thank you.
I'm just looking at the, I'm not sure. So, okay, let's see, beam. It doesn't, it's not back yet. So I know there was a discussion about the proteins, that the sources of it, and I didn't want to kind of neglect that since it was coming up as the data was being collected. Any questions about that, Bolin teachers?
I can share. Let me do this. This is the website for Seattle Structural Genomics Center for Infectious Diseases that I'm sharing. So this is where we look to get our target proteins from. And again, you can literally just do a search. You know, so you can see we were looking at tRNA methyltransferases. You do a quick search, and it gives you a list of the proteins and what's available or not. Oh, there's something here available. And it tells you whether or not it's in the PDB or not. And, you know, if it's been approved, if there's stuff that's happening with it. And then if you're interested in them, what you do is you just click on, you know, the particular protein, and then you can actually just set up an order. You just go right through, click on what you want, and you can order the material. The only thing they ask is that there's a contact person at your district. I usually use my assistant superintendent for curriculum, and they're just like, oh, you're doing research, great, and they sign off on it. And then that's just to show that it's going to like a legit person, I guess. And then they just send it to you by FedEx. It's shipped in ice, and it's usually overnight. It's about $100 or so for shipping. And we get the proteins, we put them in the freezers, and we're good to go. And then, you know, they're in nice little tubes, and we can start using the protein right then and there. We don't have to worry about purifying it. Usually we'll do some screens, which we'll get into a little later on in the week, but it's really easy to get. It's really not a hard thing to get at all. It's pretty straightforward. Go ahead, Alita. Yep.
I was just going to add that if you go that route, make sure that you have a very cold freezer at your school.
Yes.
Because proteins are temperature sensitive. So if you store them long term at 4 degrees, they might start to degrade, and then they degrade, and then they don't, as you know, they're gone, and then you don't really get any crystals. So they, you know, most schools cannot do a -80, but if you have something -20 or even cold, -20 for some short term, that might work. Something to keep in mind when you order this protein. Some schools also look at commercially available proteins to Sigma or other companies. Oh, Christine, a freezer. So you need something very cold, and it doesn't have, it has to be something that could perhaps be a -20 degrees or a little colder than that. Because proteins will, to keep the protein stable for some amount of time. Otherwise, if you store them in, let's say, in something that is not as cold, they will degrade over time, and you will lose protein. And then your crystals may not form.
It's not perfect, but if you look into buying a vaccine freezer, they look like college freezers, college refrigerator size. They usually sell them to doctors' offices, but they don't have a defrost cycle. That's kind of one of the. You just can't use like a home ec refrigerator because the freezer will go through a defrost cycle, and that could also cause a lot of problems.
Yeah.
So they do sell. I think I found it under a vaccine freezer for like a doctor's office. It's -20, but it never goes through that cycle. And the proteins have been doing okay in there. It's not probably ideal, but it's doable.
Yeah.
Mm-hmm. Yeah, and some schools, some teachers look for commercially available proteins like through other companies like Sigma, so they get the powder, and again, store at cold, -20, and they tend to. There's another source as well. The challenge with the powder is that you have to figure it out, do a good research amount to find out what are the buffers that you need to solubilize this protein to make that protein go into solution. And that's something that will require a background information too.
Now, just something with Seattle too, they're very helpful. The protein that we were looking at, the Mycobacterium paratuberculosis one, I had noted that it was crystallized. So I reached out to them and said, you know, I see that this was crystallized. Can you tell me what the conditions were? And they sent me the conditions. So instead of us having to go through this drawn out screening process where, you know, a lot of trial and error, they told me, yeah, this is what we did. And for whatever reason, they weren't able to diffract it, but we did. And so we were able to make the crystals. We got some decent diffraction on this. And this year, my students were able to actually start working on some structures, doing some analysis of the data. So they're really helpful if you know, as you're looking at things and you see, oh, if it's not like some of these, it says in the PDB, so it's already there. But anything that hasn't been, that doesn't say in PDB, it's very possible that it hasn't been crystallized and they may have the recipe for what they used for it. So that makes life a lot easier for us as teachers because, you know, they already have that information. But again, you can type in names of bacteria that, you know, you might be interested in, or there might be, you know, even these TRMDs, there are 24 of them here. Some are still available, some aren't, you know, but things come up all the time as we look through this. So sometimes we'll find things that are useful. But this is where John and I have been really trying to get most of our proteins from, just because they're purified already and it's just easier to get them. And they give us support, I said, and they're very helpful. They'll send you a tube at a time, and then I said, listen, can I have all of it? And they're like, sure. And they sent me, you know, we're gonna go to a new sample now, or we're gonna stay on this one.
We'll stay on this one, so you can go.
Okay.
Let's go to the collect.
Okay.
And the tab 1.
Okay. And so for this, we have to put in OEP. This is pin 3.
Yep.
Pin 3 / and collect, right?
Yep.
Okay.
And you can change the.
You may want to change the name of the sample, or you will just have sample in the prefix.
Oh, the prefix. Oh, this. Yes, we want to call. What do we want to do with this? We need to call this OEP1.
It's a MyPTB.
MyPTB. Okay.
The OEP11 MyPTB.
Okay, there we go. And OEP1 pin 3 collect. Okay, what else do we need to adjust on this? Anything?
I think you're okay, so you could go ahead and just hit collect.
Okay, so for everybody that's watching, we have to change this prefix. We know specifically that this is for that particular sample from PUC1 and that it's number 1. Actually, yeah, it's MyPTB. Actually, this should be, yeah, that's good. And then down here we have OEP1 pin 3. Now we're doing a collect. The previous samples, we were looking at the same sample, but we were just doing a screen. So now we're going to do a whole collection. And you can see that this is now set up over here. See this whole run over here? So this is going to take all these images and run through this. And it's expecting a runtime of about 1 minute and 14 seconds to collect all that data. So once I hit collect, what this is going to do is it's going to take that sample and start slowly rotating it while the beam is running to collect as much data as we can. A couple of other things that are here is we have our distance. We're 300 millimeters out from the sample. That's where our detector is. And then we have a beam stop here, which is the thing that stops the beam from going and burning a hole through the detector. So are we ready to hit collect? Am I good?
Yep, go ahead.
Okay. So now we'll hit collect.
You could go to the ADXV window if you wanted.
Okay. I'll switch to that.
You can go up. Yeah.
I'm going to make this collect. Okay.
Return. Yep. There you go.
Okay. There we go. So now we've collected. These are all the images that have been collected on this. And so far we're in 184. All right. We'll just click on the first one and hit load, correct?
Yep.
Okay. And then we'll run this through. And you can see that we have, doesn't look like the other stuff we had earlier, but we do have a good amount of diffraction going on in here.
Let me adjust
Right.
that quick.
Sure, go ahead. Yep. There we go. So you can see our diffraction pattern here. You can see what we're collecting. This looks pretty good. Wow. Wow, this is actually some of the best diffraction I've seen on this crystal. Wow.
Not bad.
No.
I'm
Okay.
pleasantly surprised.
Me too. So right now we're at over 500 images. It's still collecting, I think.
So
And, right?
hit the list again.
Okay.
And you'll need to scroll down
Scroll down. Okay.
at some point. So it's finished collecting everything. You've got 720. You could go up to 500 if you want.
Okay. I'll just run that one more. Oop.
Oh yeah, just push load, and then
Yep.
just do that.
Run it through. Okay, there we go. So one of the things I just want to point out is people might be noticing, okay, what's this disc in the middle here? Like you see this little bit of, it looks like an eclipse is starting to happen. Correct me if I'm wrong, that's the beam stop, right? And that's the center of the beam coming in, hitting the protein, correct?
Yeah, so that's
Right.
where, yeah, that's the center of the beam.
Okay. And then you can see that we have these really nice patterns. Like if you, as you see this going through, you'll notice there are little patterns of circles that kind of rotate around. And that's indicative of some pretty good diffraction, which we haven't really seen with this very well. So this is really good. You can kind of see how they're like right down here. There's a circle here, another one here. It looks like fireworks erupting. And that all is indicative of some pretty decent looking diffraction. So now this data is going to be saved on the computers at the Beamline. And then what we would do is then take an external hard drive and download this to that hard drive. And then the teachers would each take the files that they need and download the specific files to their own computers. So we've now collected data on this one crystal. And again, those images are showing 720 individual shots of data collectively coming from that crystal as we rotated it through. So that was a successful data collection, I think.
Yep.
Got Alita.
Nothing.
Okay.
It was. I think it was
Okay.
Kevin who was going to say something.
Oh, go ahead.
Yeah. You can go ahead.
All right. Does anyone have questions about what we just did so far, now that we've done a complete data collection?
For the next one.
I'm recording that piece, so I will share the link.
That was recorded, right? Okay. So we want to load another sample now?
101.
I couldn't hear you, Vivian.
I think she's talking to Kevin.
Okay.
Yeah, we were talking about what other samples.
Mm-hmm.
Okay.
So any one of these, like in 101, so position B, right? In 4. Yeah.
So why don't you try B4?
Okay. All right, so we're in B4. So I just click on, so I'm just clicking on sample 4 in here.
Yes.
And I can see that it has left B4, so now I'm going to click mount.
Yes.
Okay, and this will now mount that sample.
Yep.
So I'll go to the computer shot of that so we can see. Okay, and the robot removed the sample. Now it's
so
or is it cooling itself?
It's cooling itself. So I had, when we went in and added 2 more pucks, so I dried the robot. So now it's got to, because it was out of the doer, now it has to cool itself for a while.
Okay. Kevin, is there a way we can like zoom, if we wanted to zoom in just right here? Is that a different camera view?
So there's that pull down right above the camera.
Okay.
So click on that. And click on Gonio sample view.
Okay.
Yeah.
There we go. Okay. So right here, you can see that there's our pin. It's right here. Here's the pin, and
it's gone now. So
it's gone now. We'll see another one come on. So what we're looking at here, this is called the goniometer, right? That's what's holding the pin.
Yeah, there's a little magnet at the end of that.
Okay, and then the orange hose, is that the cryo stream, or that's collecting?
So that's the exhaust for the cryo stream.
Okay. And then the cryo stream is the silver tube right here at the top. That's blowing liquid nitrogen onto the crystal?
Yeah, nitrogen vapor, actually.
Okay. And that's what keeps our crystal cold. Yeah. And then this yellow striped box here, is that where the beam is coming out from?
Yeah.
Okay. Yeah. All right. So the beam's coming along this tube, goes through this aperture here, yep, comes out, strikes the crystal, and then this is the beam stop. This little, it's kind of bright, right?
Yeah.
Okay.
So there's that little arm there that's sticking out right there.
Okay.
Yeah. So the beam stop is at the end of that. And then
okay,
that bright white thing is just a small piece of foam that we stuck on the end of it to give some back reflection on the light. Just
okay.
Gives you a little bit better sample view of it.
Gotcha. Okay. Excellent. Yeah. So that's the close-up of what it looks like. So right now we're going to zoom back out, and we're going to, again, from my dining room table, I'm going to manipulate this goniometer and get that little pin to rotate. So let me back out. Let me go to the right one. I still have to look at the list here of what I have. Let's see. 3. Here we go. Okay, I'm going to go to sample low. So now I'm on a lower view here. We have a little bit of a bend in our pin. So we'll see how that affects it. There's stuff on there. Should I rotate?
Yes.
Okay. Ooh. Looks like we have a crystal sticking out right here.
Yep. So
should I zoom in?
Yep.
Okay. Oh yeah, we can see that. So there's a big crystal that's extending from the loop. So here's the loop, and we can kind of see that crystal sticking out like a unicorn. So I'm going to rotate this back the other way. So it's the crystal there.
So there's actually 2 crystals.
A bunch, yeah, yeah.
So there's, it's kind of V-shaped. So there's that one crystal that's pointing down, and then there's another crystal that's crossways to it.
Yeah. Yeah, there's one going this way.
Yeah.
Another one pointing almost like at the 5 o'clock position, right? So maybe we'll try here. Okay. So I'm going to go plus 90 to rotate. Okay. And then I'm going to go minus 90 to bring it back because I want to see that I'm on the same spot. Kevin, does it look like I'm on the crystal?
Yeah, definitely in that direction.
Okay, and then we'll go. How about this?
I think you're probably low. So I would
click above or below?
Click a little bit below, maybe halfway between the, yeah, right there. Okay, so why don't you go ahead and you can try doing some screenshots.
Okay, so we're going to go to our screening.
Collect.
I'm sorry, collect. And so we're going to go to tab 2, right?
Yeah.
Hit reset.
Yep.
Okay, and so we're going to now, this is, what puck is this one? This is a different puck now.
This is NSLS2 MX 101. Pin 4, right?
I think so.
101?
Yes.
Okay. Okay.
So this is my AB.
Okay.
With magnesium.
Let me just write this down. Sorry. Okay, so this is a different protein now. This is my AB that's mixed with magnesium. Okay, so the previous protein was from Mycobacterium paratuberculosis, subspecies avium, and now this one is from Mycobacterium abscessus. Okay, so go ahead.
So you could change, I added a 4 at the end of the screen, so you could get rid of the 4. If you want.
Oh, okay.
Like,
so get rid of the 4 for the pin 4?
No, not the pin 4, above that, the prefix.
Oh, yeah.
Yeah.
Okay. So now, do I click on 3?
Well, you could delete the 4.
Oh, okay.
Yeah, so click on 3.
Reset.
So now if you wanted to, what you could do is you could just delete this one and then duplicate number 2, and then you don't have to retype all of the
Okay. So I can hit delete.
Hit delete, and then hit the asterisk. And then
okay.
You have to, I don't know, the 4 came back, so get rid of that, and then hit return.
Okay.
And do the same thing on 2.
Yep.
Hit return. Sorry, then go back to tab 3. And then down at the start end, change the start to 90 degrees. Oh, 90.
90.
Okay.
There we go.
All right, and then you can, yeah, do collect on 2.
Oh, this says screen 4 for number 2. And 3 says the screen.
Yeah, so just go back to 2 and delete those.
Just delete that? Okay.
Okay. Okay. Yeah, and then go ahead and you can hit collect.
Okay. So we're hitting collect, and now up here, what we'll do is change this to the correct. This was NSLS2.
Just hit, if you delete all that, just hit return.
Okay.
Hit return.
Oh, okay, there we go. Perfect.
Whoops.
Ooh.
Sorry, you're at the very bottom.
Oh, there I am. Okay. There we go. Pin 4. Screening. And load, correct?
Yes.
Oh, wow.
So, twin. Or gangbusters.
Wow.
That's beautiful.
That's a real nice diffraction pattern.
Mm-hmm. It's in a way, oh, there you go.
There we go. Wow. John, nice work.
Can you let them know what makes it up pretty?
What makes it pretty is you see lots of dots that have really good organization to it. You can see that there's nice, concise dots here that form the circle, and then this kind of follows the pattern around. And even over here, you can see that each of these these run in pretty much lines with each other. There's a little bit of a curve to them, but each of these dots, you can kind of see that there's a pattern there. There's also another circle over here. And again, you see that concentric rings that are forming around it. So you have a circle here with these concentric rings, and then you have a circle here again with these concentric rings. And the dots themselves, the spots themselves, look very uniform in terms of being round. Whereas the very first collection that we did, where we did a screen, they looked very streaky. We call it chicken feet, is what it looks like when chickens scratch in the ground. These dots don't have that. They're not elongated. So this looks really, really nice. So that's screen 2. Wow. Very nice. And then screen 3 also, lots of diffraction there. Right? So I think we want to we definitely want to collect data on this.
Yeah, so let's
Right.
have another look at this.
Go ahead.
Olin, what is your diffraction there? About 1.8?
1.86, yeah. So these are diffracting very well to a very good resolution. The lower the number, the better the resolution. So we're at 1.87 angstroms there.
Yeah, so I push the detector in a little bit closer when you do the data collection.
Okay.
So that's not really a big deal. Go back to the blue ice window.
Okay.
And then go to tab 1. Then get reset.
Okay, and this is going to be NSLS2, NX 101. The trickiest part of this is the naming. You're making sure that you're consistent. Did I do that correct? NSLS2, MX101, pin 4, collect.
Yep, I think so.
Okay, all right.
Hit return. And so now under the distance, why don't you try changing that to like 250?
Okay.
Okay.
Right.
And you can go ahead and push collect.
Okay, so now we're going to collect data on that crystal, and we'll go back to here. And this we can change to collect. Sometimes we misname these, and then Kevin has to go and search through to find it. Yep, it's starting to collect. We can see we've got 11 images already. So we'll let that run for a few, and then we'll look at the movie and see how this click list then load.
Can you go to the web view?
There we go. We're good now?
Yeah.
right. So we're playing our movie, and it's still collecting, but lots of diffraction. Looks like we got some overlap too. Maybe picked up 2 crystals.
Yeah, that could be.
Yeah, I saw that a little bit too.
Yeah. Well, something I want to show. Let's see.
Stop.
Right here, I just want to stop this. When we get this little bit of like a halo on the top and the bottom, that indicates a little bit of the loop maybe getting in there. Sometimes we see that.
But you are also
Right.
seeing in that area that you had some influence of the second crystal.
Right. Right. Yep. Okay. Yeah, that's right. Because right when that popped up.
If you go back, you will see that.
Yes.
You have two structures here.
Yep.
It looks like in the center between these 2 halos, it looks like you have a chicken net.
Yep.
Right?
Yep. They're all sort of interacting with each other, kind of almost canceling each other. Right.
Hitting both crystals because they were in the same plane in the loop, right?
Right. Yeah, because you can see when that popped up, and then that goes away, and then we get a more uniform diffraction pattern coming up. So what do we got so far? 241 images. Okay.
Yeah, push list again.
Okay. Okay.
So Bolin, there is one position right now. Okay. It's gone. Where you can see a 4-fold symmetry.
I'm going to go back a couple of images.
I'm not sure.
Is it right before the halo?
Yeah, it's before the halo.
Okay. I'll just go back to the beginning.
More.
I'll play it, and then when you see it, tell me to stop.
Stop. So you see, like, probably because of the space group, like it has, if you rotate 90 degrees, you will always see the same set.
Okay. Is this right here about this image right here?
No, if you go and look at the center, you have like a bunch of spots.
Mm-hmm.
And then on the first outer circle, if you walk like about 90 degrees, no, the first circle. Can I take the mouse?
Yeah, go ahead.
So you have here this inner circle, and then you have this first other circle.
Okay.
And the other circles kind of, it's not 100%, but it is pretty much there.
Okay.
Okay.
All right.
You can get it going.
Okay. There we go. Yeah, there's where you see that kind of that overlap with the 2 crystals. Beautiful. You can see in the magnified view where those spots show up in that area. Nice spots, nice dots, nice density there. John, do you have a structure for the magnesium yet, or we're still working on that?
Let's see.
I think Vivian has some of the groups.
Okay. Oh, working on the magnesium. Okay.
Yeah, with my AB.
Right.
Oh,
Possible.
you want to put another one after this one?
I think that would be good. It's 11:42, so I think we have more time for one more, right, Vivian?
Just one more.
Mm-hmm.
Okay. Okay.
So we can put one that has an SAH bound or the finifungin. John, which one do you prefer?
The SFG comes out pretty good.
Sorry?
Okay.
The Steampoinian, SFG.
The sinifungin?
Yeah.
Okay.
Mm-hmm.
I will never
So
learn how
that
to say
would
that.
be on C14.
C14. Okay.
And just to give an idea to the participant, these are two ligands that the groups from Pennequart are looking at that possibly bind to this MyoB protein. So they're looking at these two different ligands. So they did the crystallization with the ligands, not a soaking, right? John, it was just a co-crystallization with the ligand itself.
Yeah, so SFG or Steampoinian, what I can never pronounce. It's a known inhibitor. It's very common. It's just like basically an analog of its natural ligand, SAM. So it wouldn't work as a good antibiotic because it would basically bind anything that SAM binds. But it's good for structural analysis. And they've done it with several TRMDs, but no one was able to get it with this one. So we had tried a few different conditions and kind of got lucky, which is kind of why I recommend it. Sometimes, you know, if you find something that others have done and kind of work off of that, sometimes you do get lucky. Yeah. And then MTA is, it's in the pathway of it being recycled. So we were just curious to see if that would bind back. Yeah.
Oh, there you go. Yep.
Yep, that's a typical SFG. That was with condition 15. Normally it's done with condition 4 and it gives you like nice big crystals, but
right.
So you vary in the chemistry of your crystallization. You can also vary the shape of that crystal.
Yeah, so it's one of those stories that basically no one ever did it with SFG because normally they use this condition 4, which makes nice crystals, but it didn't work with SFG. So we tried a second condition that someone had previously at Spark had found to form crystals, not great crystals, but crystals. And this time it did work with SFG.
Wow, nice. Looks like you've got actually, it looks like there's a split maybe in the crystal here. So
sometimes there's doubles.
Yeah, there's doubles. Yeah, so yeah, that looks like there's two. It's like when we rotate it, you can kind of catch it a bit. Kevin, does it look like I'm on the crystal when I rotate 90?
Yeah, maybe a little bit low, so you could try just bumping it up a little bit. The other way. Sorry.
Oh, other way.
The other way.
Maybe a little slightly more.
That's probably too fine now.
Yeah, I'm off the.
Let me mouse.
Good.
Kevin is aligning it.
Yeah. It's close. Yeah. So one of the things that's nice with this beam line is when we're working remotely like this, it's actually a nice thing. It's also something you got to be careful of. We have equal access at the same time. So I can move my mouse around on here and click around, and then Kevin or Vivian, while they're there, can also just use their mouse and do the exact same thing. So we're basically working off the same screen at the same time. But we also have to be careful because if I click somewhere accidentally, I could throw something off. So we've learned to just be real careful with our clicks and not to jump around and move too much while we're trying to make sure things are aligned. All right. And this was,
So you could go ahead and set up do the screening
okay.
shots for this.
Okay. So this is, Vivian, what's this puck now?
So 10.
So this is pack 102.
102. Okay.
NSLS2, MX 102,
Okay.
pin 14.
102, pin 14. Oh.
Yeah.
It doesn't like me to use my backspace. Okay. 2, pin 14. Okay.
Hit return.
Okay. And this we can hit reset, delete, right? And then we can just.
Or you don't have to really retype too much stuff. You just got to change the 101 to 102. And so.
Okay. 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 Hit return. Yep. Okay. And detector distance is good. We're at 300.
Yeah, that's fine.
90, 390. Okay, good. So collect.
Yep.
All right. Okay. Okay. Interesting. Okay.
Another nice one.
Yeah.
And then you could probably hit list again and get the 90-degree.
That's a nice one, Bowen.
Yeah, that is.
Let me.
I think it's 3.
Are we good? Is it not?
None.
No. Oh, there we go. Okay.
Okay. Yeah.
Yep, there we go. Looks good.
Okay, so yeah, you can
Right?
go back and set up the data collection.
Looks nice.
Yeah, that looks really good. Yeah. Okay. So we're going to do this one. All right. So this is, we have to reset.
Yes.
Okay. And we're going to do 102. And this is 102. Okay.
Then hit return.
Okay. Do that. We're at 250.
If that's okay. Yeah.
Yep. Okay. And ready to collect?
Go ahead.
Okay. So now we're going to collect and we'll switch back to the other view. Not ready yet.
Okay, so it's just started, so.
Okay. Oh, here we go. All right, so we'll give this a minute or two, or a minute to collect. So basically it takes about a minute or two to get a whole data collection on a crystal once it starts running, correct?
Yeah.
So that's pretty fast. There we go. There's our movie. So again, what's kind of neat about this is in real time, we're watching this happen where we're shooting the crystal with the X-rays. We're getting this diffraction data to come up. And we're going to get, you know, several hundred images within about a minute and a half. And then this information gets fed through the programs that we have at the beamline, and that will be converted into programs that can be used so we can generate a 3D structure. That looks good. Now you figure a typical beam time runs 8 hours. So after doing this for a few hours, between watching it and doing it and students and teachers taking turns, you start to kind of get the idea of what you need to do with this. And you start to get the sense of what you're looking for, what looks good, what doesn't look good. And so we become our own, oh, you can see a little bit of overlap there, not bad. That looks great.
One thing that I want to add to the beam time, you know, the time at the beam that we haven't discussed and probably will be discussed as the beam time does happen, is the metadata collection. So in addition to having the spreadsheet, we keep a notebook with detailed information regarding what samples were what data, from which samples data was collected from. And if data was not collected from IA sample, we say we note why it was not collected. It was a poor diffraction. Sometimes the pin falls. Like last beam cycle, I used this very inexpensive glue to glue the pins in, and everything fell. So we do keep metadata about the energy that it was used, the detector distance, and if that varies, we make notes of that as well. I know we have not discussed that in this, but I would say that as you participate in data collection, we will go and we will talk about those details, but metadata is also kept during beam time collection as well. All right. Is it all collected, Bobby?
It's done.
I think so, yeah, 720, cool. Yep.
All right. So this is our last data, right? Collection, because we are almost noon.
Yeah, it's 11:56. Yep.
So Kevin, you know, the samples are then taken out, right, Kevin, from the doers and stored, or if you are done with your data collection, we pick the pucks and clean them up and keep the pins to reuse for the next time we do, you know, another sample set. It needs to be done. So I think that, you know, the center gets unmounted and then put it back in the doer. I think tomorrow what we plan to do is to go over the data analysis. So Kevin will join us in the morning to give us an overview. So this is how you take it from that, what is at the end station at the beam. And then we will have Christopher Giannarotta, who is a student at Stony Brook, and he is going to demonstrate how some basic steps in the data analysis software that we use to look at this, to create from those dots to a 3D structure. Very simple. as a simple, as a quick overview. Those data, those programs are available to the public. So we will share the links of those programs tomorrow. Any questions to Kevin or Bowman or Vivian? I don't want to forget Vivian or John or the world. Okay. I'm going to stop recording for a moment. If I know how to do this, hold on.